What is going on, guys? Welcome back. In this video today we're going to learn how to do hyperparameter tuning for neural networks using SciKeras. So let us get right into it. Alright, so we're going to learn how to do hyperparameter tuning for neural networks in Python today. Now, what are hyperparameters? Ordinary parameters are things like weights and biases. These are the things changed and tweaked while training the neural network. And hyperparameters are things that we configure about the model. For example, how many hidden layers we want to have, how many neurons per hidden layer we want to have, what activation functions we use, what the learning rate is, what initialization functions we use, things like regularization parameters and so on. So things that define the model architecture and the functions and parameters used for the individual layers and optimizers and so on. These are the things that we can tweak to optimize the performance of the model. Now, hyperparameter tuning means trying different configurations and figuring out which one works best. And this is what we're going to do in this video today. I want to start right away with a simple example where we're going to train a handwritten digit classifier without hyperparameter tuning. And then I want to show you how we would do hyperparameter tuning on this kind of model. So what we're going to need for this video today is TensorFlow. We're going to say pip or pip3 install TensorFlow. And we're going to use a package called SciKeras, which basically will take the model and turn it into a scikit-learn classifier. And then we can do grid search, which we did in a lot of videos on this channel already, where I showed you how to do hyperparameter tuning for scikit-learn models. So for example, just as a quick side note here, if we have something like a random forest classifier from scikit-learn, we do have different hyperparameters for these kinds of models as well, as you can see here, and estimators, max depth, min sample split, and so on. So different things that we can tweak about the random forest. How many trees do we have in there? What's the max depth of a tree, and so on. These are things that are not the decision tree parameters themselves. So it's not the decision-making process. It's not the thing that we actually use to come to the prediction, but these are things, parameters or hyperparameters about the training process, about the model architecture. And the same thing is possible for neural networks. And one more thing, maybe we do that using cross-validation usually, or a validation set. So we evaluate this not on the final test data, because that would be misleading. If you optimize your hyperparameters for the thing you're testing on, of course it's going to perform quite well because you optimize the parameters for the testing set. So what you usually do is you either do a training validation test split, or you do a training test split and then you do cross-validation, which we're going to talk about here in a second. But I want to go with the first simple example here, and this is going to be just a handwritten digit classifier. So we're going to say from TensorFlow .keras.models, we're going to import a simple sequential model. Now let's see if the autocomplete is going to work here. I don't think so. So let's just type it out. Sequential. From TensorFlow Keras layers, we're going to import a couple of layers here. We're going to need the dense layer, the flatten layer, the input layer, the dropout layer, and the batch normalization layer. Now, the reason I'm including so many different layers is because these are also going to be hyperparameters that we can invent. For example, we can build a neural network and we can say one of the hyperparameters is, do I want to use dropout regularization? And if yes, what's the dropout rate, and so on. So I can specify all these things as hyperparameters, and I can say train the same model but without dropout or with a different dropout rate and see which one performs best. That's the basic idea here. So from TensorFlow, we're also going to say from TensorFlow Keras.optimizers, we want to use the atom optimizer. From TensorFlow Keras.datasets, we want to use the MNIST dataset. And then we also just need from TensorFlow Keras, I think utils, import normalize, which is going to allow us to normalize the data. Now to get the data, we do the following thing. We say xtrain and ytrain, so the training data here, and xtest and ytest is equal to the MNIST .load data function call. So this is going to return the data. Now this data, if we look at it, it's going to contain RGB values. Now it's not visible here because we only have the pixels that are that are 0, but here you can see we have values between 0 and 255, which is not optimal for a neural network. So what we want to do is we want to normalize the x data. We do that by saying xtrain is equal to normalize xtrain, and we do that on axis equals 1. We do the same thing for the test data. Now we don't normalize the y data because these are just labels, so we do that only for the pixel values. And then we can get into the model. Now we're going to use a simple model here just as a baseline, and then we're going to go into hyperparameter tuning. So what we usually do is we say we have a model, sequential, there you go, and we have a list of layers. These layers, let's say we start with a simple input layer. The input layer will have a certain shape. In the case of the MNIST data, it's 28 times 28 pixels. We then flatten this image data to make it one-dimensional so that we can feed it into the next layer. So we use a flatten layer to do that. Then we use a dense layer just so we can have some intelligence in there. Let's say we use 32 neurons. The activation function here is going to be rectified linear units, so ReLU. And the end is going to be an output layer with 10 neurons. The activation function here is going to be softmax to give us a probability for each class. And that is a simple neural network here. Without hyperparameter tuning, without anything, this is just a basic version. And then I also say model.compile. I'm going to specify that I want to use an atom optimizer with a learning rate of 0.001, which is a good default. I'm going to use as the loss function here the sparse categorical cross entropy. And I'm going to say that the metrics I'm interested in here, this is going to be equal to accuracy. All right, so that is going to create and compile our model. Ignore the warnings here. On my system, I have some problems with my setup. Let's just ignore that. But I have the model now, and what I need to do now to train this is I have to say model fit xtrain ytrain. Let's say we do this for 15 epochs. And then the training process is going to start. You can see it's training. You can also see the training accuracy and the training loss. You can see it's going down, so the training is converging here. And in the end, what we're going to do is we're going to evaluate this on the test data. Now, we're not going to do that for the hyperparameter tuning, but we just want to see how well does our model perform if we go with this default setting. So we're going to say model evaluate xtest ytest, and what's the problem here? Oh, I think I messed up because here I'm normalizing xtrain again, so we need to run this again. Actually, we just need to run this again. I think this shouldn't change much. Let me just see. What's the problem here now? Oh, yeah, obviously it doesn't work like that. We need to do it like this, and I think now it should work. So is this loss or accuracy now? I'm not sure. Let me just run this again. So just to explain what the problem was, I used the xtrain here in the normalize function, which means the xtest data was the xtrain data normalized, which means that it doesn't have the same dimensions as the y data or the same size as the y data, which is why it's incompatible. So I'm training it here again. And then we're going to get a baseline of performance. So in this case, we can see, yeah, this was the accuracy. So this is a 96.6% accuracy, a 0.11 or 0.119 loss. And this is now our baseline without hyperparameter tuning with a very simple model. Now, what we could do, of course, manually is we could open up an Excel sheet and we could say, okay, let me track the different configurations. So I want to see if my model performs better if I add a second layer, for example. And if I say that I don't want to have 32 neurons, I want to have 64 neurons. That's a possibility. Then maybe here I don't want to use the ReLU function, but the LU function or CellU function or something like this. And then I can do stuff like tweaking the learning rate. Maybe I want to have 0.005, and maybe I want to have a dropout layer here, and so on and so forth. I could do all of this manually, but then I would also have to cross-examine. So maybe it's better when I increase the number of hidden layers and the number of neurons, and I add a dropout layer. But is it now because I added a dropout layer, or is it because I increased the number of neurons? So these things are difficult, or it's not really difficult conceptually, but they're tedious to do manually. So you don't want to do all of these configurations manually. Maybe you make mistakes. So what you want to do is you want to do something called a grid search, or you can also go with a randomized search, but we're going to go with a grid search here. The idea of a grid search is that you specify a parameter grid. As I already mentioned, I did a couple of videos on this channel where we do this in scikit-learn. So you specify a parameter grid. Let's say we have, for example, here, we could call this n hidden, the number of hidden layers, and then you pass a list to this grid. You can say I want to have 1 hidden layer, I want to have 2 hidden layers, and I want to have 3 hidden layers. These are the amounts that I want to test here. Then we want to have the number of neurons per hidden layer, for example. And then we could have something like 32, 64, 128. And then maybe I want to use dropout. This can be a Boolean, so that could be true or false. And so on and so forth. You define a parameter grid, and what you do with a grid search is you try all the combinations. So you try 1 hidden layer with 32 neurons and a dropout layer. You try 1 hidden layer, 32 neurons, and no dropout. You try 1 hidden layer, 64 neurons, and a dropout. And you try all the combinations, which means the higher or the larger your parameter grid is, the more combinations you're going to have. So this can actually be quite expensive, so you should really try to not enter too many values and too many hyperparameters here, because otherwise you're going to have to try a lot of different things. And if you're training a large model, a complex model on a lot of data, this is going to take forever. So make sure that you choose the things that are really relevant and interesting to you. But how do we actually set this up? Now, what we need to do is we need to define a function that builds our model. So I'm going to add here just a simple heading to say now we're going into hyperparameter tuning. And what we're going to do here is we're going to set up a function build model. And this build model function will take parameters. And these are going to be the parameters that we're going to be able to tweak. For example, n hidden equal to 1. For example, n neurons equal to 32. For example, learning rate equal to 0.001. These are the default values. For example, kernel initializer, which is the initialization of the weights and so on, of the parameters. Let's say the default is HE normal. Then we could have something like use dropout, or let's call this add dropout is going to be equal to false by default. Add batch normalization equal to false by default, and so on. And these are things that we can now extend. So you can have many, many different parameters here. And these are then going to define how you actually build your model. So these are now the parameters. Let me zoom out a little bit. And what we're going to do now is, based on the input, we're going to define the model. So I'm going to say here model is equal to sequential, which means it's going to be a sequential model. And then we're going to say the first model the first layer definitely has to be an input layer followed by a flattened layer. This is it is regardless of the hyperparameters, we need to have an input layer of shape 2828 and then a flattened layer to make it compatible with the following layers. So I'm going to say the model is definitely going to get a new layer, which is going to be an input layer with a shape 2828. And it's definitely going to be followed by a flattened layer. And the next thing now is we want to add the dense layers, so the hidden layers. How many and how large? So this depends on the hyperparameter n hidden and on the hyperparameter n neurons. So what we're going to do is we're going to say for I in range, or actually let's call this for layer in range, n hidden. We're going to go through a loop, which is going to add to the model a dense layer with n neurons, and an activation function, which could, of course, also be a hyperparameter. You could try to add this as a hyperparameter, but I'm just going to go with ReLU every single time here. And we also want to specify the kernel initializer, which is going to be the kernel initializer. So this can also be a hyperparameter. Then, after each layer, do we want to add a dropout layer or not? If at dropout, we want to add a dropout layer. Model add dropout with In this case, we don't have a hyperparameter for this, so another hyperparameter could be the dropout rate. You could just go ahead and add it here if you want to. I'm just going to always use 0.2, just to keep it simple here. And if at batch normalization, we're going to say model at batch normalization. And then in the end, this is also something, regardless of the hyperparameters, we want to have a final layer, which is going to be a dense layer with 10 neurons, and it's going to have the activation function softmax. And that is now the function. The final thing is we need to compile it and we need to return it, because this is the build model function. So model compile optimizer is going to be equal to Atom with a learning rate equal to learning rate, and a loss function equal to the sparse categorical cross entropy, and the metrics we're interested in equal to accuracy. Yeah, that's the model, and then we return it. This is now a function that we can use to build a model. So I can go ahead and say build model, and I can say n hidden equals 3, n neurons equals 64, and this will return a model to me that has these this architecture that I'm passing here. And this can now easily be turned into a scikit-learn classifier, which is what SciKeras is actually for. SciKeras takes this now and translates it from Keras to scikit-learn, so that we can use the grid search CV from scikit-learn and apply it onto our neural network. How do we do that? We do that by saying from SciKeras wrapper import Keras classifier, and we say that the Keras classifier is equal to a Keras classifier based on the build model function. No module SciKeras wrapper, so I probably need to install this. Okay, why is that not? All right, guys, this is embarrassing. I spent way more time than I'm willing to admit here reinstalling SciKeras, reinstalling Keras, looking at Stack Overflow posts, asking ChatGPT just to figure out that I'm missing an S. It's SciKeras.wrappers, plural. This kind of stuff can cost you a lot of time if you don't look at your code properly. So from SciKeras.wrappers, import Keras classifier. Keras classifier is equal to Keras classifier, and we pass our build model function, which turns this into a scikit-learn classifier that is now compatible with the scikit-learn ecosystem. So we can use grid search CV, which, if you Google it, grid search CV belongs to scikit-learn and is a cross-validation grid search hyperparameter tuning class, so to say. This is what we're going to use here. So what I can do is I can now do the same thing that I can do with any other scikit-learn classifier. So Keras CLF fit xtrain ytrain. I can pass the epochs here as well, 15. And this works now like any other scikit-learn classifier. Of course, now the methods are changed because we're not going to do evaluate, we're going to do score. This is the scikit-learn way to do it. So I can say Keras CLF score x-test y-test, and I get an accuracy as a result here. So what we're going to do now is we're going to do grid search on this scikit-learn classifier. So I'm going to say here that the parameter grid is going to be equal to. Now, the important thing is that we need to provide a specific prefix to actually target the hyperparameter. So we cannot just say n hidden. What we need to do is we need to say model underscore underscore n hidden for all the hyperparameters. For example, 3 hidden layers versus 4 hidden layers. Then I can do model underscore underscore n neurons, and I can choose between 128 to 56, for example. And then I can move on, model underscore underscore learning rate, and so on and so forth. I can say 0.001, 0.005, 0.01. And I can do that with all the different hyperparameters. I can say model underscore underscore kernel initializer is going to be equal to HE normal and to glorot normal. I hope this is how it's pronounced. And I can do that now also with the booleans for at batch norm and at dropout. The problem is, and you will see that this is a problem, maybe let's actually add all of them. So let's say model at dropout true false, then at batch norm true false. With this parameter grid now, we can boot up a calculator and we can calculate how many different runs we have here. So we have two different parameters for the hidden layers times two different for the neurons, three different learning rates, two different initializers, two different settings for the dropout layer, two different batch norms, already 96 runs. So we have to fit the network 96 times. Now we're running also cross-validation. The idea of cross-validation is I take the training data and I test on sections and evaluate, or train on sections and evaluate on other sections. Now to make this representative, we do this with different folds, so to say. And you can't just do it once, you have to do it multiple times. So if you do 3-fold cross-validation, you have to multiply this number by 3. If you do 5-fold cross-validation, you have to multiply it by 5. Which means that if I want to do a 5-fold cross-validation on this parameter grid here, I have to do 480 times the same thing that we did before. Now in this case, it's quite fast. I can do that. I can go get a coffee or something, or maybe 2 coffees or 3, but I will get a result in a decent amount of time. If training the neural network, this is my Jupyter notebook, this was not what I'm looking for here. If I have to do this for 1 day, if I have to train a neural network for 1 day to get a result, this will take 480 days, which is more than a year. So that's not necessarily feasible. So it makes sense to only pick parameters here in the grid that are reasonable, or to do something like randomized search CV, or to just reduce the amount of data that you use, or to do less epochs. The problem with less epochs is if you reduce the learning rate, of course, convergence is going to be slower usually, but it can also mean that the convergence is going to be better. So you're going to get a better result in the end if you do it for long enough. So going with just 5 epochs is maybe not a good strategy here. For the sake of demonstration here, I'm just going to go with 2 parameters here. I'm going to just go with the hidden layers and the neurons. I'm going to leave everything the same or at the default value just to show you that it works and how it works. And then you can run this with all the different parameters here if you want to. So we're going to say the Keras classifier is equal to a Keras classifier of build model. Now we're going to set a couple of default values here. So I'm going to say that n hidden, or actually, no, that's not what I want to do. Actually, what I'm going to do is, or what I can do is I can say that since some of the parameters are not part of the parameter grid, maybe I want to do this not with the default learning rate. I can pass a learning rate here, which is equal to 0.05, for example, or 0.05. So I can do that without having it be part of the parameter grid. So it's always the same, but I can specify something else than the default here as well, if I want to do that. I'm not going to do this now. I'm just going to pass the method here again. And, or actually, did I do? Yeah, I trained the model. So I'm going to define it here again. And the grid search will now be the following. The grid search will be an instance of, and we need to import this from scikit-learn, or sklearn, dot model selection. We're going to import the grid search CV, the grid search cross-validation. And we're going to initialize it here with the following settings. We're going to pass the classifier, the Keras classifier, the parameter grid. We're going to set cross-validation equal to 3, and we're going to set verbose equal to 2. This just means we're going to see more information about the process. We're going to get more information. And then what we can do is we can just say grid search dot fit the training data. And what you're going to see right away here is it calculates the amount of fits. In this case, since we only have this parameter grid here, we have these 4 candidates, and we have 3 times, because we do a 3-fold cross-validation. In this case, we get 12 fits. As I said, you can calculate this yourself. How many different configurations do you have here, and then how many times, or how many, what's the number of folds that you want to use in your cross-validation. So in this case now, it's going to just train the model 12 times. And as a result, we're going to see, you also see, by the way, here the configuration. So you can keep track of the process. If you set verbose to 2, you can see the first run here is 3 hidden layers, 128 neurons. And then we get a certain accuracy and loss. Then we do the same thing and the same thing, and then we get, we're done with the first candidate. And then we do the same thing here with 3 hidden layers and 256 neurons, and so on and so forth. And what you get in the end is the best estimator. So you can say grid search dot best estimator to get the final result. You can also say, I think there's best param, so grid search dot best parameter to get the best settings. And in this case, the best settings were 3 hidden layers with 256 neurons. So 3 hidden layers seems to work better than 4, but it's better to have more neurons rather than less neurons. Now, one rule of thumb here when you do these parameter grid hyperparameter tuning things is if you get a value at the border, at the boundary here, it makes sense to test for further values. So since 3 now here is the lowest value, it makes sense to do another hyperparameter tuning with 2 and 3, for example, or with 1, 2, and 3. And here, for example, it makes sense to get rid of 128, but to go maybe to larger values, 512 and 1024, which is going to be too much, but you can try. And in the case that you get the best result again with 1024, it makes sense to go further, to get rid of these 2, and to say I want to test with more than that, 2048 and so on. You can do that, and it makes sense to just explore the different hyperparameter space, but of course it's a trade-off. You need to know, or you need to determine how complicated or how much time you want to invest into this to get a better performance. Now we can actually get this best estimator. We can save it as a model here, and we can say that we want to evaluate the model on the test data and see what kind of accuracy we get. In this case, we get 96.47, which is, I think, worse than what we had before. Yes. And the reason for that is probably that our parameter grid was not very good. So we probably should check for 1, 2, 3 layers with 32, 64, 128 neurons, and with maybe also dropout and batch normalization. But that's the basic process. You take a model, you build a function around it where you can specify the architecture. You can customize everything in this function. The important thing is you get parameters and you get a model as an output. Everything in between is customizable. You take this function, you feed it into SciKeras, you get a scikit-learn classifier, and then you use either grid search or randomized search CV, and then you have your hyperparameter tuning. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.